measurement accuracy from the lab last week. It didn't affect the grade or anything, but in case anybody's interested, it was group 3 and Wednesday that had the best accuracy. They were 0.008% off. So I'm using your total station distances, my total station distances. So just in case you're interested, but everybody did very good. I've got lab 1 and lab 2 graded. I'm still working on the homework. I'm going to distribute the grade reports and whatnot in lab this week. Your second homework is getting assigned today at 5 p.m. and it will be due next Wednesday at 1 p.m. Okay? Just to make sure that we're up to date on the schedule, we have a celebration of learning coming up here in a couple weeks. So we celebrate on September 20th, and so on September 13th, which is next Wednesday, we're going to have exam review. In exam review, the way I do exam reviews is you come in for the first a few minutes. I'll talk about the format of the exam and what's going to be on it, and then it's up to you to ask whatever questions you want. Some of you had me for class before, so you kind of get the drill. But the idea is to come in prepared to ask whatever questions you would like. If you want to go through lecture, homework problems, what have you. So the exam will primarily cover homeworks 1 and 2. There will be some questions probably related to what we're doing in lab, but what we're doing in lab follows what we're doing in lecture, so there's not really anything additional and what have you. Sound good? All right, let's get into today's topic. So last time we talked about horizontal distance measurement. Today we're going to talk about vertical distance measurement. And so what we're specifically focused on for the next couple of levels is one of the most fundamental operations in land surveying, which is performing a differential level. Okay. Before we get into differential leveling, I want to go through a couple of terminology items and some definitions, just to make sure that we're all on the same page with what we're talking about. We mentioned early on in the semester, we started talking about just the basics of measurement, and we said that there's really there's no way of measuring a value to its true value. I mean, we can get close, but we can never get to that 100% true value. But we do have to have something to go off of in the land surveying. And so one of the things that we will utilize as land surveyors is what's called a benchmark. A benchmark is a relatively permanent point where the coordinates or the elevation is known or assumed to be known. And I'll show you some examples of some benchmarks here in a bit. But the idea essentially is that a benchmark is a permanent monument that a land surveyor can reference when they're performing a land survey. And so they can reference coordinates based on that. And there are benchmarks all over the place, and I'll show you, where you can find them and whatnot. I might use the term vertical datum. So a vertical datum is basically just a coordinate system or a reference axis by which we reference coordinates. And so since we're talking about vertical distance measurement, what I'm talking about with a datum is elevations. Okay? So when we reference elevation, what would an elevation of 0 be? It would be sea level, right? So what do we mean by sea level? Like, what is sea level? We have to have a common reference datum. And so what we use is the North American vertical datum, which was established in the late 80s, early 90s. And what we have a station in Quebec, Canada, and we use that station to reference at the elevation of 0. So whenever you pull up the elevation, let's say of a given benchmark, that's what it's going off of. And when we say elevation, what we're talking about is a vertical distance from that datum to a point in question. Okay. These are some examples of what benchmarks look like. You've probably passed them and just didn't really notice them. They sort of look like these plugs usually set in concrete. I couldn't help but pull this one up. This is one that you can actually find at Disney World. You can see that they actually put the Mickey Mouse thing and whatnot. But essentially what they are is a fixed point where the elevation is known. And when we say point, like for example, if we look at the Mickey Mouse, when we're talking about this point right there. So that point, the idea is if you're performing a land survey, you essentially can use this point as your XYZ coordinates to begin your survey. So for example, if I wanted to determine the elevation, let's say of this first step, I could reference it based off of the elevation of that point right there. And that's kind of the idea behind a differential level that we're going to be performing today. You can look up benchmarks pretty easily. I have this website right here, and you can look up the controlled data sheets. And I've got a couple of slides to kind of show you what this looks like. So I went ahead and went to this site and just basically put in Huntington, West Virginia, and you can see all of the benchmarks located. This is pretty much near to Marshall's campus. Different benchmarks are going to be set for different data. So some of them are only going to contain vertical control. Some of them are going to contain X, Y, and Z. Some of them might be for GPS and what have you. So let me kind of show you one. So if we look right here, so this is the Huntington area, and I'm going to show you what one of these data sheets looks like for the benchmark right here. This is the one at Riverfront Park. So when you pull the data sheet, what you'll see is it sort of looks like this computer readout and whatnot, but there's a couple of lines that are really key. So for example, if you look here, so we have NAD 83, this shows this data 38, 25, 25, 62 west, 82, 26, 34, 74 west, north and west. What do you think this first row is?
It's coordinates.
And specifically, I'm talking about latitude and longitude, right? So this is the latitude and longitude of this monument, and then NAVD 88, the height in meters and in feet. So we can assume that that point in question has an elevation of 547.76 feet. And some of the data sheets actually contain photographs. This one did as well, and I put those photographs here so you can actually see where the benchmark is. So this is the flood wall there at Riverfront Park, and they actually have the benchmark inset into the wall, so you can actually go there and see the point in question. Some of them have photographs, some of them don't, but they're all going to contain lat long and elevation and whatnot. Does that make sense? So the idea is that if you're performing a survey, you can tie into that, you can reference off of that and begin your work. So I just want to make sure that everybody's kind of clear on what a benchmark is. We are going to use a benchmark today. I have a point here in front of Mara Library. We're going to use that as our reference to determine the unknown elevation of a given point. The lab this week is going to be determining the elevation of the bench on the memorial fountain. That's what we're going to be doing today. Okay, so let's talk about differential leveling. Okay, so a differential level is a surveying procedure where what we're doing is taking the elevation of a known point and trying to use that as reference to determine the elevation of an unknown point. In order to perform a differential level, you don't need a total station. All you need is an auto level, a tripod, and the level rod with the rod level with it. So the amount of equipment that we're going to need today is far less than we needed in our previous lab and what have you. Okay. Now I want to show you how a differential level is performed. So I've got some sketches here on the board, and I kind of want to give you an idea as to how this works. Okay, so what I have here on the board is a plan view and a profile view, and this profile view is just sort of focused on this loop right here. But let's say we're starting, let's say this is our loop. Okay, so I've got benchmark A, and let's assume for our discussion purposes that the elevation of benchmark A is known. And I'm just going to make up a number. Let's say it's 345.60 feet. Okay, and let's say the goal of the survey is to determine the elevation of station C, what have you. Now, normally what you would try and do is perform as few measurements as possible and measure that as directly as possible. But what you'll find is that, let's say there's a big building in the middle of the way and you can't shoot that. So instead what you have to do is go around, and you're going to see that very viscerally today because that's what we're going to be doing in lab today. We're going to be surveying from the front field of Mara Library all the way to the memorial fountain. There's going to be stuff in the way, so you're going to have to figure that out. So what we'll do is we'll perform a series of intermediate setups. Okay, so maybe what we'll do is we'll start off by, setting up the instrument right here. So we'll set up our level, right here. Okay, and the very first thing that we're going to do is we're going to set up our level, get it set up and whatnot. And one person's going to be using this, one person's going to be running the rod, using the rod. And they're going to stand here on this, and then we're going to take a reading like that. Okay, so the level or the person running the instrument is going to read the rod right here. Now we call this a backsight. Okay, so let me show you what's happening here. Let's show you this on profile view. So here's the benchmark. Here's what we're going to call a turning point. You're going to see this turning point here in a second. So we've got the instrument set up right here. Okay. Now what we're going to do is we're going to set up our level rod right here. It's going to be level. And then what we're going to do is we're going to take a reading. Okay. And I'm going to call that a backsight. Okay. Now, let me ask you a question. Let's say that this backsight, let's make up a number. Let's say that's 1.55 feet. Okay, let's say that's 1.55 feet. If the elevation of this benchmark is 345.66 feet, and I read this, what does that tell me? Well, what it tells me is the height of the instrument, right? It'll tell me how tall the instrument is, or what's the elevation of the instrument. And the elevation of the instrument is going to be whatever the elevation of our benchmark is, plus whatever that backsight is, because we're going up. Does that make sense? With me so far? Okay. Then what will happen is the person carrying the rod, the person running the instrument, they will stay right here. The instrument doesn't move. The instrument sits right there. Then what happens is the person running the rod will then take the rod over here, right? Okay, and what happens then is the person running the instrument will turn and they will read on this point right here, and I'm going to call that a turning point. Okay, call it turning point because you're literally turning level. And so what we'll then do is read the rod, and we read the rod and we call that a foresight. Okay, all right, so we run the foresight. Okay. Now let's say we do this foresight, we do a reading, and let's say it's, I don't know, 6.75 feet. What does that tell me? Well, from this first measurement, I took the elevation of the benchmark, added the backsight, and that told me the height of the instrument. I can take the height of the instrument, subtract the foresight, that tells me the elevation of this turning point. Does that make sense? And so the way that a differential level works is it's going to be like this. You're going to take a backsight, then you're going to turn, take a foresight. Then once you've taken the foresight, what happens is you take the instrument, you move it, let's say somewhere right here, you then take a backsight on the turning point, go back up to the next station, take a foresight, and it's sort of this leveling loop, right? So, you know, you start out instrument here, backsight, foresight, instrument here, backsight, foresight, instrument here. You have this sort of like chain link that you keep going until you get to a point where you have a setup right here. You have your backsight and then your foresight, and you end up back where you started. Does that make sense? So that's kind of the idea of a differential leveling loop, okay? Now, a couple things about differential leveling loops. So first off, unlike the last lab, this is going to be kind of weird, but it doesn't really matter where you set up the instrument. What matters is that the instrument is level, that it's free from obstructions, so you can actually see your backsight and foresight, and that your distance between those 2 points are relatively equal. So we don't need the plumb bob to get the instrument over a specific point. What matters more is that your benchmarks and your turning points are well established. Okay. Again, like I said, the idea is that you're going to perform this in a loop. Again, you know, setup, backsight, foresight, setup, backsight, foresight, setup, backsight, foresight. So you have this sort of loop setup. Okay. Everybody with me kind of on the idea so far? Okay. Now, before we get into the calculations, I kind of want to make sure that we're clear on how the notes are set up, because the notes might be set up in a little bit of an odd fashion the first time that you see it. So I want to make sure that that's very, very clear. Okay. So what should happen first off? So your very first row. So what I've got here is my table, and don't worry, your lab handout will have the guide on how to draw your table. But I kind of want to go through this with everybody. Your very first row will be the benchmark that you're using. That's the starting point, the known piece of elevation, okay? So we're going to start out with our benchmark here, and we know the elevation is 345.60 feet, right? I'll just leave the feet off because everything's going to be in feet. With me so far? Now, if you recall, the very first thing that we did is we did a backsight onto, we set up our instrument and we did a backsight on point A, right? So we did backsight, then foresight, backsight, then foresight. So we backsighted this point. I think the number I used was 1.55 feet, right? But then the next thing I did is I did a foresight. I didn't do a foresight on this point. I did a foresight on turning point 1, right? So my foresight, it doesn't go here, it goes down here. So my foresight of 6.75 goes here, okay? The idea is that when you set up your table, so what do we have? We have a benchmark, a turning point, our station in question, and then we went back to the benchmark. Again, we start and stop at the benchmark. So the idea is that as you set up, the very first row should not have a foresight, and the very last row should not have a backsight, okay? So when you're setting that up, that first row foresight should be blank, that last row backsight should be blank. With me so far? Okay. And so what you'll do is you'll say, okay, I'll set up backsight this, foresight this. And you'll notice I'm skipping a row, right? So what we'll do, we'll backsight this, foresight this, backsight this, foresight this. Okay? So why am I skipping a row? The reason that I'm skipping a row is because if these are my backsights and foresights, in between, these correspond to the setups, right? So this row is set up 1. This row is set up 2. This row is set up 3, okay? And so the idea is, okay, here's how this works, okay? So let's work through this together, all right? As we said, so we start out, we observe benchmark A, we take a backsight. And if you remember, we add that backsight, and that'll tell us the height of the instrument, right? Okay, so where do I put that? I put that right here. So I take the elevation, add the backsight, and I get this term here. What is 345 plus 0.6? It's 347.15. Does that make sense? So that's going to be the elevation of that setup. And then what I do is I take the height of the instrument minus the foresight, and I'm going to get what? 340.4. That's now the elevation of turning point 1. You see the pattern here? See how what I'm doing is in between the rows, so I take this elevation, add that backsight, and I get 341.65, right? And then I take this instrument height, subtract the foresight, and I get 355.15. I'm sort of going through the arithmetic fairly quickly, but does that idea kind of make sense? Okay, take the elevation, add the backsight, and I get 347.06. So that plus that is this. Take the height of the instrument minus the foresight, I get 345.54. Okay, everybody with me so far? Okay, does anybody see a problem right now? You're shaking your head, yes, what's the problem?
Well, it's 355 and it should be 335. That's it.
Oh! That is correct. That's what happens when you're going kind of fast. Thank you. But that's not the problem though. Does everybody see the problem? They don't line up, right? So look right here. So, well, let me show you something, okay? What I'm going to do, I want to show you something just to make sure. So see how what we were doing with this column is we were adding everything in this column and we were subtracting everything in this column? Everybody see that? So I'm going to do something real quick. Let's add up all the numbers in this column. So I got a sum down here below. So that plus this, I sum that up, I get 14.71. Okay? I do the same thing for my foresights. Okay? Sum up this, and this, and I get 14.77. Is anybody seeing a problem with that?
The difference between those two is.
Okay, I'm glad you saw that. Okay, you're 100% right. Okay, so the big main problem is that we started at benchmark A and we ended at benchmark A. So we started with a known elevation of 345.6 and we should have ended with 345.6, but we didn't, right? There is error present in the calculations, and that is going to happen to every group in here. It's just going to happen, right? I mean, think what you're doing. You're in the lab, you're setting up the level, you're reading that rod, it's got to be level, you're doing it over and over again, you're going to have error, right? But the problem is, like, this is wrong, right? This starts 345.6, it should end at 345.6. So what we need to do is we need to figure out a means of adjusting these elevations such that it closes, such that it starts at 345.6 and ends at 345.6. And that's one of the things we're going to discuss today. Now, what you pointed out was 100% correct. What's the difference between these two? 0.06. What's the difference between these two? 0.06. That process is what's called a page check, and it's something that I want everybody to do in lab today to make sure that when you're performing your calculations, that the difference between these two matches the difference between these two. Does that make sense? Okay. All right. So here's the procedure, right? So you locate a point of known elevation, which I'm going to give you. You set up your tripod and your auto level between that and a turning point. Backsight the known elevation, foresight the turning point. Then the rod person stays here. You move the instrument and you keep repeating the process until you get back to the initial benchmark, closing the loop. Does that process make sense? Okay. Now, what we were talking about, what you identified is what's called a page check. So the error of closure, and I will probably call that closure or misclosure, it all means the same thing. The closure can be calculated two different ways. You can take the sum of the backsights minus the sum of the foresights and get negative 0.06, or you can take the final elevation minus the initial elevation and get negative 0.06, okay? If you do that calculation both ways, you should get the same answer. That's what's called a page check, and I want you to do that today just to make sure that you don't have any math errors when you set everything up, okay? Everybody with me so far? Okay, any questions on the idea? Okay, all right. Now, with differential level surveys, with vertical elevation measurements, we have different orders and classes of the survey, okay? Now, we classify a survey based on essentially two quantities, based on how much misclosure we have and the distance traveled. Now, for this lab today, we're not going to measure the distance traveled. The reason why is because there are two ways of determining this adjusted elevation. One is using an equal adjustment, one is using a weighted adjustment. The equal adjustment is easier and doesn't require distances. And I want you to get used to doing a differential level, so I'm going to try and make it as easy as possible during the first lab. But you do need that distance in order to compute the closure or the classification or the precision of the survey. And don't worry, we'll get to that in lab here in a bit. Okay. Now, in order to compute the allowable closure error, we use the following expression. So we take the closure and we compare that to the square root of the distance traveled and this constant according to this table here. So in order for you to have, let's say, a first order class 2 survey, your M value needs to either be 4 or smaller than 4. Don't worry, I've got a couple examples here in a second to kind of show you how this works. The big item to keep in mind is that this is in metric, so you got to do some unit conversions here. Okay, everybody with me so far? All right, so let me kind of show you how this works. So let's do a couple of these quick error examples. This is not incredibly difficult. I think you'll see how this works. I just want to make sure that we're all kind of comfortable with this part here. So let's start off with the first one, and this is the one that I think is much more in line with what you would need to do in the real world. So let's say you've run a differential leveling loop from an established benchmark that's 2 miles away, okay? Now the mist closure is 0.056 feet, okay? So for this, example, let's consider that C is the closure error, which is 0.056 feet, okay? Now the distance traveled, okay, let's make sure we're paying attention. If a differential leveling loop is run from this benchmark to a point that's 2 miles away, what's the total distance traveled? Keep in mind, it's a loop. 4 miles, right? So we're going 2 miles there and 2 miles back, right? Remember, it's a loop, right? So we're going to assume that the distance traveled is 4 miles. Okay, does that make sense? Right, because it's there and back, right? Now, we've got to convert this to metric, okay? So what we'll do for the C quantity is we'll say, okay, C is 0.056 feet, and what we'll do is we'll say there's 12 inches in 1 foot, and we'll say there's 25.4 millimeters in 1 inch, okay? And anybody got an answer for me on this one? Because everybody brought their Casio FX115 ES Plus or similar scientific calculator to class, right? Of course. That should just roll off the tongue. I mean, come on, what are we talking about here? Because everybody brought their calculator to class, right? Everybody brought their calculator to class, right? Everybody. I'm waking everybody up. We're going to be outside here in a little bit. At least some of you are. Anybody got an answer for me on this? 17.07. So we'll call it, 17.069 millimeters. And then for significant digits, we've got 2 significant digits, so we'll call this 17 millimeters. For the miles, so K, we got to get that in kilometers. So I can never remember the miles to kilometer one. So if you have that written down, that's great. But I'm going to have to go the long way. So the long way, we got 5280 feet in 1 mile. So unfortunately, I got to go the long way. So we got 12 inches in 1 foot. We got 25.4 millimeters in 1 inch. And then there's 1 million millimeters in a kilometer, or 10 to the 6 millimeters in 1 kilometer. I got to go the long way because I can never remember that. All right, so I'll go ahead and do this one for you. So we chug this out, and we're going to get about 6.437 kilometers, which chugs out to 6.4 for 2 significant digits. Okay. And so the idea then, remember our expression is we're saying that C equals M times the square root of K. So the idea then is M is C over the square root of K, which is 17 over the square root of 6.4. What do we get when we check that one out? 6.4. All these calculator slides. Anybody got an answer for me?
6.72.
We'll go with that. 6.72. Do I have a second?
Yes.
Okay. All right. So 6.72. All right. So what I'm going to do is go back to the classification table here. So in order to have a second order class 1 survey, we need a value of 6 or less. We're not there. We're not quite there. We have a value that's higher than this, but it's not less than that. So that means we're in second order class 2. Does that make sense? Okay, so this is going to be second order class 2. So we'll call this. All right. With me so far? All right. What do we think? So far, so good? That's not too difficult, right? Okay, all right. We'll do one more just to make sure we're comfortable with this part. So this one's a little backwards, okay? So we've got a differential leveling loop that we're running from an established point to a point that's 3.5 miles away, okay? So my loop in this case is 7 miles. And then we'll do the same thing. And then this is 10 to the 6 millimeters, 1 kilometer. All right. I'm getting 11 something. Anybody else getting that? 11.265. That right? So to 2 significant digits. So 11 kilometers. So this one's asking something a little different. This is, let's say, before the job is conducted. Let's say the specifications indicate it's got to be a second order class 1. So second order class 1 is asking what's the allowable misclosure. Okay? So if we go to our specifications, we find that for second order class 1, we need an M value of 6, right? An M value of 6. So an M value of 6 means that our misclosure is going to be computed as n square root of k. So 6 times the square root of 11. And what is 6 times the square root of 11? It comes out to about like 19.8997, something like that. And so what we'll do, but keep in mind that's in millimeters. So we'll call that, I don't know, 20 millimeters. But 20 millimeters doesn't really help us out if we're surveying in feet. So what we're going to do is we're going to say, okay, we have 1 inch is 25.4 millimeters, and 1 foot is 12 inches. And so when we check that out, we're going to get something like 0.0656 feet. And to 2 significant digits, we'll say that C is 0.066. So whenever we perform that survey, that closure, or that difference between this and this, can't be greater than that in order for our survey to be second order class 1. Does that make sense? Everybody okay with that? Okay. I didn't think these calculations would be terribly difficult. I want to make sure that we're comfortable with the adjustment part. And that's kind of what I want to spend the rest of the lecture discussing, is these adjustment mechanisms. But so far so good? Okay. So what we're going to do is we got to fix this problem. We got to adjust our elevations such that we close our loop. Okay. And there are 2 means of doing that. One is an equal distribution of error, and the other is a weighted distribution of error. We'll talk about weighted distributions on Monday. Okay, so let's go back to our loop. This is the same loop I have here on the board. Okay, and the page check, as I mentioned, so we have our closure, which is the sum of the backsights minus the sum of the foresights. We got negative 0.06. And then we can also check that with the final elevation minus the initial elevation. That's what we're going to try and adjust. So sometimes students get a little concerned about the signs. So with both methods, let's just keep this simple. See how these elevations, see how this elevation is lower than this one? So what that means is that all of these elevations, these intermediate elevations, this one and this one and this one, need to be raised a little bit such that this gets to 345.6. Because this is our known elevation. This value down here needs to be 345.6. So what we're going to be doing is we're going to be raising these elevations a little bit. Okay. Now, how much error do we have? We have negative 0.06, right? That's our error, right? Now, how many instrument setups did we have on this level? How many instrument setups? 3. So an equal distribution of error would mean we have, this is our error, we have 3 setups. So we need to do an adjustment of negative 0.02 for every setup. That's an equal adjustment of error. Okay, so that's what an equal distribution means. I've got some formulas here, but I really think that once you see the pattern, you'll go, oh, okay, the pattern's usually a little easier to follow than the formula. But the idea is that what we do is we take we compute an adjustment, which is the misclosure times the number of setups. Now I've got a negative in here because what I got to do is I got to flip the sign. So my error is negative 0.06, so my adjustment needs to be positive to bring everything up. And so what I will do is I will recompute these elevations, okay? And I'll recompute these elevations by adding this adjustment, okay? So let me show you how this works, okay? So here's this table here on the screen, I've got it here on the board. So let me show you how this works. So let me grab these markers here, and let's walk through it, okay? So I'm starting out, so my adjusted elevation, this needs to be 345.60, because I know that's not going to change. That's my benchmark. That's my known elevation. So how do I compute this elevation right here? How do I do it? Okay. Well, I start off with 345.6. Okay. What am I going to do? I'm going to add my Backsight. My Backsight was 1.55. I'm going to subtract my Foresight, which is 6.75. And that's how I got this number, right? That's how I got that number. But now what I got to do, add my adjustment, right? So instead of 340.40, I'm going to get 340.42. Does that make sense? So that's what I'm going to do right here. Okay, so there's my adjustment. That's how I get this first one, right? Okay, so that is how I get this value right here. Okay, so how do I compute this one? Okay. Well, what I do is I take my adjusted elevation, and I say, okay, let's add the Backsight, subtract the Foresight, and then add another adjustment, right? And so I don't use this number, I use my new one. Take my new elevation, add the Backsight, subtract the Foresight, add the adjustment. And what do I get? I get 335.19. Okay? With me so far? So again, I'm basically doing these adjustments all over again. I'm doing these elevation calculations, but I'm referencing this new column. Okay? So what do I do down here? Take my new elevation, 335.19, add my Backsight, subtract my Foresight, and then add my new adjustment. Somebody calculate that out. Tell me what you get. My new elevation, add the Backsight, subtract the Foresight, add my adjustment. What do I get?
$345.6.
Exactly where I started. Does that make sense? What do you think? Is that complicated? That's basically what we're doing, okay? And to make sure that we're all comfortable with this, I got an example we're going to do here in a second. Okay, so we're gonna do one more. We're going to do it fully, start to finish. We're going to do it together, okay? All right. I'm going to make this table a little bigger to make sure that we're all comfortable with this. Okay? So what we're going to do is we've got a leveling loop that we've got a table set up for, and we're going to perform all of our calculations necessary for heights of instruments, elevations, adjusted elevations. We're going to do this start to finish. Let's see how we're doing. Okay? So we started out with a benchmark of 100 feet. We took a Backsight of 5.51. So what can I do with that? Elevation, Backsight. What can I measure now?
I have to look at your elevation
And where does the height of instrument go?
in between.
In between the rows, right there, doesn't it, right? So I take my instrument height and I put that right here. So if I start at 100 and I add 5.51, I'm going to get 105.510 right there, right? I take my instrument height, I subtract my Foresight, and that tells me the height of this turning point, and 105.51 minus that is going to be 102.260. Sound good? And so we continue on with this pattern. Take that, add the Backsight, and I can put that right there, and I get 108.79. Is everybody following with me on this? So remember, you always have that level split right there. And if you need, what you can do is you can say, okay, this right here, this is the height of instrument 1. This is the height of instrument 2. You know, except if you need to do that. Okay? So I take the 108.79, subtract my Foresight, and I get 98.29. Right? Take that, add my Backsight. Now I've got 102.61. You see where I'm coming up with these numbers? Right? So I'm taking my elevation, adding my Backsight to get my instrument height, then taking the instrument height, subtracting the Foresight to get the elevation. So that's why we write the columns like this. The Backsight has a plus, the Foresight has a minus. That's our way of remembering that. So 102.61 minus 6.67, this is 95.94. Then what do? Take that, add the Backsight to get the instrument height. Take the instrument height, subtract the Foresight to get that. Make sense? Now this loop is off. This is an off loop, right? We have some big numbers to kind of make sense of this, okay? So how can we check to make sure that we've done this correctly? Let's sum up our Backsights, let's sum up our Foresights, right? So I've got these Backsights, take that plus that plus that plus that. I sum that up and I get 19.63. Am I right on that?
Yes.
Okay. And my Foresights, what do I got for my Foresights? $28.31. Okay, so one way that you can do a page check, so here's a simple way of doing a page check. Take 100 feet, which is our starting elevation, right? Add the sum of the Backsights minus the sum of the Foresights. So this is 100 feet plus 19.630 minus 28.310. What do we get when we do that?
98.32.
Which is the same thing we got at the very end, right? Okay, so that's your page check to make sure that you've done everything correctly. Okay. So far, so good?
Yes.
Okay. All right. So check this out. So our closure is the sum of the Backsights minus the sum of the Foresights, which is 19.630 minus 28.310, which is going to be negative, and it's negative 8.68. So far, so good? So if it's negative 8.68, my adjustment is going to be the opposite of that. It's going to be plus 8.68 feet divided by how much? 4, because there were 4 setups, right? There's 4 setups. So 8.68 over 4, what is that, like 2.17?
Yes.
2.17. Here, let me add my 0 there.
Okay.
plus 2.170 feet. So far, so good? Okay, so 2.170 feet. Let's put that up here on the board. So plus 2.170 feet. Okay, so how do we go about this? So we've got our elevations. We're going to try and fix this. So how do we compute this cell? So we take our elevation, we add our Backsight, subtract our Foresight, and add that. When we do that, what do we get right here? I want to make sure we're all on the same page with this. So again, we're taking our elevation, adding our Backsight, subtracting our Foresight, adding an adjustment.
104.43.
104.430. Do I have a second on that? Okay. What about our next one? So we take our new elevation, add our Backsight, subtract our Foresight, add an adjustment. What goes here? And don't worry, if we're going fast with this, y'all are going to get practice with this here in a bit. It's much more low pressure. What goes right there? Again, we take our elevation, add our Backsight, subtract our Foresight, add an adjustment.
What was our adjustment?
Right here, sorry. I'll put that right here, 2.17.
102.63.
102.63. Do I have a second on that? All right. And so, take this again. Add our Backsight, subtract our Foresight, throw an adjustment. Anybody getting like an idea of what program we might want to use for this?
Excel.
This is an Excel-friendly
Maybe
calculation.
MATLAB. I think everyone wanted MATLAB.
All right, hold on. Let's bring it up. Oh, it's right here.
Let me have it.
What do we get here? So we take our Backsight, take our Backsight, add that, subtract our Foresight, adjustment, what goes right here?
102.45.
Do we have a second on that?
Yes.
All right, what about our last one? We take our elevation, add our Backsight, subtract our Foresight, throw an adjustment. What do we get? 100 even, right? What do we think? Now, I know we did this kind of fast, and my main reason for doing this kind of fast is because you're going to do it again on your own. I'll be here to help, but you're going to be doing it here in about 10 minutes for you folks in the Wednesday lab and tomorrow for you folks in the Thursday lab. So you're going to do this again on your own here in the next few minutes for the most part. So does that make sense? All right, hold on. I want to take a step, take a pause. Does anybody have any questions about this? Now, what we're doing, just to be clear, what we're doing is an equal distribution of error. What we're going to do next on Monday and in your next lab is a weighted distribution of error, where the adjustments per setup are different. But I want to wait until we've got a little bit of exposure and experience with this. With that, that's all I got for you Wednesday, folks. Up here in the next 10 minutes. Otherwise, I'll see you tomorrow. Great.